Cool. So, hey, we are 2 weeks down. We're already a sixth of the way through this quarter. I will just tell you that this past 2 weeks went so much faster than the previous 2 weeks when there was absolutely nothing to do but sit around at home. So, I mean, I will take it. I'm busier than you could imagine. Like the workload for me is like 5 times as much as normal. So, but I'm not complaining. It just, hey, it is what it is. But speaking of workload, how's the homework going? Anything we want to talk about?
Can we say number 40?
Yeah,
I'm sorry, which one was that, Trey?
42.
Yeah, I want to see 42.
Can I see number 8?
And if I could see 29.
42, 8, 29. Did I catch all of them?
Yeah.
Yeah.
That
Okay,
sounds
and
good.
then remind me what section this is. 2-4?
Yep. Yeah.
2-4.
Okay, so let me share my screen. And again, I don't know if we're going to do all of them all the way through, but we'll at least talk about all of them, get you to a point where you should be able to finish, okay? All right, so hopefully you see my screen. All right, so are we on the right page here? So number 8, we want to solve this initial value problem, the y prime minus xy equals xy to the 3 halves.
Yeah.
All right, so let me go ahead and write that down on my board, and then we'll go to the board. All right, so I'm going to stop sharing. All right, so to the board. So we've got y prime minus xy equals xy to the 3 halves. All right, so what do we want to do first?
Identify your different parts, or whatever you want to call them. P of x,
Identify
Q of x.
V, your P of x, your Q of x, and your N.
Okay. So how about this? What method are we trying here?
Bernoulli's.
Okay, so this is a Bernoulli because of our form. All right, so for Bernoulli, what do we need? I heard you say P of x. What's P of x?
So it's going to be a
It's
y
minus x.
P of x equals minus x.
So P of x is minus x. Is what we're multiplying to the y. All right. What about Q of x?
X.
X.
All right, and where's that coming from?
Coming from the right
other
side.
side.
That's
Yeah,
being
right side.
multiplied into the y to the 3 halves.
Right, it's what we got multiplied by y to a power. So that's our x. And then what's the one other thing we need?
We need the power of that y,
N.
which is 3/2.
Okay, so we want the power of this guy. And we call that n, was that right?
Yeah.
I forget what the book said. So it was n. So we've got then n is equal to 3 halves. All right, so we look at it, we recognize it's Bernoulli, and that's because of this y to the n. And then we go and we steal this information. Okay, now what?
You need to find y1 and u.
All right, so what's the process for this? How do we find y1 and u?
Set it to the homogeneous.
So if you look at just the
0.
homogeneous, we have the y prime minus xy equals 0. Then the solution to that is going to be e to the negative integral of p. So p minus x, its integral is going to be minus x squared over 2. We then make it negative and take e to that power. So we get y1 equals e to the x squared over 2. All right, so far so good?
Mm-hmm.
Now what?
You need to find u.
All right, so now we want to look for that integrating factor thing we multiply by. How do we find u?
U prime over un equals p of x or g of x times y1 to the r minus 1.
Okay.
Or n, sorry, you guys are using n.
Nope, that totally works. So we're going to find that guy u. And again, what we know is that u prime over u to the 3/2, that's going to equal x times y to the 1/2. So basically all you got to do, if we want to kind of speed up to a generalization and make this a little bit maybe easier, not having to remember a formula. So what we have over here on the right, so this x to the, or times y to the 3/2, just decrease that exponent by 1.
Hey, Bruce.
Yeah.
Is that times y or times y1?
Sorry, yeah, y1.
Okay.
So it's that same thing, but just decrease this by 1. That's 1/2. And you put the original power on this guy. All right, so this is our form for Bernoulli. So now we'll put our y1 in there. So we're going to get u prime over u, 3/2, is equal to x times e to the x squared over 2 to the 1/2. So that's going to be u prime over u to the 3/2 equals x e to the x squared over 4. And the whole point of this is now this is separable. This is something we can integrate to find our u. So if we separate that, we're going to get du over u to the 3/2 equals x e to the x squared over 4 dx. And now we want to integrate both of those things. I'm going to write over here our y1 because we're going to need that. All right, so questions before we finish the sucker off and get you. So far, so good? All right, so now let's integrate. So this is just u to the minus 3/2. So we're going to get minus 2 u to the minus 1/2. The other side, thank God for this x. So we can do a u substitution, otherwise it'd be something that we can't integrate. But this is going to give us an e to the x squared over 4. But we need a 2 on that because we're off by just a little bit. So we get 2e to the x squared over 4. And it's here that we should put our c. So we're going to go ahead and put plus c. All right. So now let's get rid of the minus 2. Let's divide by minus 2. So we get 1 over the square root of u is equal to c minus e to the x squared over 4. We'll square both sides and then invert it so that u is equal to 1 over c minus e to the x squared over 4 squared. So that's what u is going to look like. The specific C we'll find out in a second. But as for right now, that's what we should get for our U. All right, so good so far? Any question? All right, so then what do we do with this U?
Put it in the equation, y equals u, y1.
Right, so the whole point of this U business, the integrating factors, is that this is what we multiply to the known solution. So y then is going to be u times y1. So we're going to get e to the x squared over 2 over c minus e to the x squared over 4 squared. Isn't that pretty? Nice, pretty little function. It's not pretty, but we know that it's the one that if we go back to this differential equation, satisfies it. Anything of this form. So the last step is to find C, figure out what C has to equal. So we'll just go ahead and finish this off. We're close enough. So we do know an initial condition. We knew that when we plugged in 1, we should get 4. So that's going to give us 4 equals e to the 1/2 over c minus e to the 1/2 squared. Or not 1/2, sorry, 1/4. This one. So c minus e to the 1/4 squared is going to equal e to the 1/2 over 4. If I take a square root, I get c minus e to the 1/4 is equal to e to the 1/4 over 2. So c is equal to 3/2 e to the 1/4. So we'll go ahead and put that into here. So we get y equals e to the x squared over 2 over 3/2 e to the 1/4 minus e to the x squared over 4 squared. And I'm going to leave it like that. Feel free to do any kind of nonsense algebra. But by this point, we don't care about algebra anymore. I mean, you guys probably haven't cared about algebra in years, but. All right, so is that good for 8?
Yeah, I must have just exactly messed up my algebra somewhere.
Well, hopefully I didn't make any mistakes. I was just about to say, hopefully I didn't make up any mistakes, which sometimes I do. But. All right, so okay for that one? So let's go take a look at number 29. Going to go back to share screen again. All right, so for 29, we've got another differential equation here, and it says we want to solve the given homogeneous equation implicitly. So implicit means we don't care about solving for y. We just want to get something that relates to x and y that's a solution. So I'm going to go ahead and write this up on the board, and then we'll switch it back to the board. All right, so back to the board. So we've got y prime x minus y
times natural log of y minus natural log of x equals x. All right, so what are we going to do?
Is this a nonlinear homogeneous?
What do you guys think? So it's definitely nonlinear. So is it homogeneous nonlinear, meaning can we write it y prime equals a function of x over y?
I believe yes. I'm gonna go yes.
You're going to go yes.
I mean, I did it that way.
All right. Well, it looks like Trey's backing you up. He just said yes. So let's see if we can make it as y over x. So the first thing I would do is take care of this natural log stuff. Since I've got a log minus a log, I can combine that as a division. So we get y prime x minus y times the natural log of y over x equals x. And I definitely like that because I'm starting to get y over x. So now let's keep moving this as a y prime equals. So we'll divide by that natural log. We'll get y prime x minus y equals x over the natural log of y over x. I'll add y over there. So adding y to both sides is going to give me y prime x equals x over the natural log of y over x plus y. And then I'm going to divide everything by x. And so the x's cancel for this first term, and then the y over x gives me y over x. And that definitely looks like it's the homogeneous nonlinear. All right, so cool, homogeneous nonlinear. So now what do we do?
U sub.
Yeah, we let u equal y plus x. So let me go ahead and do that right here. So if we let u equal y plus x, or say y over x, not y plus x, u equal y over x, then this differential equation now is going to look a little different. Remember, the y is u times x, which means y prime is going to be u prime x plus u. And that's going to equal 1 over the natural log of u plus u. And this guy is now separable. So if we subtract u from both sides, multiply by the natural log of u and move the x and everything, we're going to get natural log of u du is equal to 1 over x dx. And now we're ready to integrate. But before we integrate, any questions on the steps? All right, so integrating natural log of u gives us u natural log of u minus u. That one, you actually would have to do parts, unless you remember just the integral of natural log. So it's u log u minus u. And then on the other side, we get the natural log of x. But let's put on our plus c. And now we substitute back in our u equals y over x. So we get y over x times the natural log of y over x minus y over x equals the natural log of x plus c. And since they just ask us to write this in an implicit form, that's good enough for me. I mean, the one thing I might do is multiply by x just to get rid of the fractions, but we're just looking for implicit form, so we're good. All right, so is that better for 29? Cool. So let's go look at number 48. All right, so I'm going to share my screen again. And I lied. We're going to look at 42, not 48. All right, so here's 42. We've got y prime equals 2x plus y plus 1 over x plus 2y minus 4. Now, it does say, let's use the method suggested by exercise 40 to solve the given equation implicitly. So let's go back and look at 40. And 40, notice that what we've got here is just a linear function of x and y divided by another linear function of x and y, which is what we've got. And it says it can be transformed into the homogeneous nonlinear that looks like this with big Y and big X using the substitution x equals big X minus x naught and y equals big Y minus y naught, where x naught and y naught are suitably chosen constants. So you got to love that. I'm going to put some constant in there that's going to make it so that this is the right form. All right. Well, if you look at that, first of all, you notice that 42 is exactly the form of 40. So we've got A is 2, B is 1, alpha is 1, C is 1, D is 2, and beta is minus 4. So let me just go ahead and write this up on the board.
Hey, Bruce, it's a +1 on the top.
Thank you. Okay, so I think I've got all the important information on the board here.
Hey, Bruce, I had a question.
Yeah.
I was looking at that the proof section of that, and I saw the AD minus BC, and it reminded me of the determinant of a 2x2.
Yep.
Is there any sort of connection, or?
Absolutely.
Got
Yeah.
it.
So think about where that came from with the determinant. So the AD minus BC not equaling 0, what that meant.
Let me talk to you guys for a little bit. So where that came from was actually looking at a system, looking at that 2x2 system. And the determinant, of course, the big thing was equal to 0 or not equal to 0. And how that related to the systems was solution or no solution to the 2x2. And so these A, B, C, and D, they are coming from a system of equations. And basically, we just need to have that system to have a solution, which is then if you go to the TFAE list that you guys learned in linear, having a solution means the determinant is non-zero. So that's the relationship there. And the fact that you saw that is good, that you're recognizing the AD minus BC coming from the determinant of a 2x2 system.
Yeah, there's like a lot of areas where it just sort of peeks through with linear into diffy Qs. So it's really cool though.
Yeah, and if you end up taking more math, like Thea, I don't know how far you're going to go, but if you keep taking more math, linear algebra permeates its way into just about everything. There are times where you'll go, oh my God, we're just finding a vector space, you know, like this is a basis of the space or whatever. And you really, even if you went back in time, you could kind of throw those linear terms into things we've done before. We didn't call them that. You know what I mean? Like we never talked about solution spaces.
Yeah.
But they mattered back in the day. Like, go back to a great example. Go to when we were talking about like lines in space, right? And you would write the solution as some vector times t. You'd do it parametrically.
Yep.
Well, that you found a basis for that one-dimensional space.
Yep.
Right? Or with planes, how it required two of them, so we would have a t parameter and an s parameter. Well, the t and the s, those were your arbitrary constants thrown onto those other vectors, because now it's a two-dimensional space and all that. So now that you've seen linear algebra, you will see it places. You'll know it when you see it, basically.
Got it.
All right. So we good? Let's jump back and see if we can take care of this.
So what we need is we need to find x naught and y naught. We need to figure out what those values are. We need to choose them appropriately so that we can actually do this substitution and get something that's the homogeneous nonlinear. So how do you think we're going to go about that? And you're going to hate the answer. We're going to do algebra. We're basically going to look at what does x naught and y naught have to be so that when we put them into this, we get exactly the form of our original differential equation. So big X is equal to x plus x naught, and big Y is equal to y plus y naught. Let's put those things in and figure out what all the different things need to be. Now, of course, A, B, C, and D are still the same A, B, C, and D. Those didn't change. But the x naught and y naught, they're going to come from the 1 and the -4. So let's change these to being the values. So we have 2 times x and 1 times big Y, 1 times x and 2 times big Y. And let's see what happens when we put these expressions in and what that forces the x naught and y naught to be. I'm just going to rewrite these over here so that we don't forget them. All right, so if we put that in, we're going to get 2 times x plus x naught plus y naught over x plus x naught plus 2 times y plus y naught. And so distributing and everything gives us 2x naught, or 2x plus y plus 2x naught plus y naught. And on the bottom, we're going to get x plus 2y plus x naught plus 2y naught. And from this, we're going to get a system. We're going to get 2x naught plus y naught has to equal 1. That's the constant on top. And then x naught plus 2y naught has to equal -4. And I think at this point, you can really see, Theo, what you were talking about, why that has to not equal 0. Because this is like the coefficient matrix would be the 2, 1, 1, 2. We know its determinant can't equal 0, which back to the proof. All right, so let's see what that tells us. X naught and y naught have to be. So -3. So I think y naught is -3 and x naught is 2. Double check me on that, but I think that's right. So that means that the substitutions we're using, if I come back up here, let me put the numbers, we're going to get little x is big X minus 2, and little y is big Y plus 3. So that's the substitution we're going to do. And when we do that substitution, we get this form right here. So I wanted to make sure that we have that substitution up here because we're going to need it when we go back. But how are we doing so far? All right. So basically that means we just need to solve this homogeneous. So we'll go ahead and divide by big X. So we get dy dx is equal to 2 plus y over x over 1 plus 2y over x. So again, we'll do a u sub. So if we let u equal big Y over big X, same kind of story as before, we're going to get u prime big X plus u is equal to 2 plus u over 1 plus 2u. Subtract our u. So we're going to get u prime x equals 2 plus u over 1 plus 2u minus u. Getting a common denominator. So we're going to get u prime x. That's going to equal, so let's see, we subtract u, subtract 2u squared. So I think we get 2 minus 2u squared over 1 plus 2u. Which then, when we separate, gets 1 plus 2u over 2 minus 2u squared du is equal to dx over x. And now we get to have integration fun. Obviously, that right-hand side is easy. The left-hand side, oh, that's not terrible. I was worried we were going to have to do partial, or partial fractions. But we're actually, oh no, we are.
I just put it into Symbolab and I got 1/4 quantity multiplied ln of u plus 1 minus ln u minus 1 minus 1/2 times ln 2 minus 2u squared. Yep, that put the big bracket around the minus ln u minus 1 part. Yep, there we go.
Okay, so that looks good for the integral of this.
Yep.
So then that equals natural log of big X plus c. Beautiful. And then, of course, there's the matter of plugging back in. This wasn't an initial condition problem, right? So what we're going to have to do is replace in for the u. It's going to be big Y over big X, but we want to get those back to little. x's and y's. So this u in terms of the originals is going to be y minus 3 over x plus 2. And I'm using the substitutions we found for the x and y. Put those back. So take that, put that everywhere there's a u. And then the other thing we have to worry about on the right-hand side, that big X has to go back to a small x. So this will be the natural log of little x plus 2 plus c. But other than that, just fire this into all the spots for you. We could actually do a lot of algebra to help us out. Because like these logs, we can combine them into one with division. You multiply by 4, get rid of all the fractions. Then we're going to have a 2 times this natural log. Okay, we'll bring that 2 in as a square. And then we've got a 1 log minus another log. So we could actually put those all together and get a single log on this side. And then we can get rid of that using E and all that good stuff. So it actually is going to simplify a bit if we do algebra. But like I said, I'm not doing it. I'll leave that for you guys, if you want. All right, so is that better for 42? So this is just another way that you can do some sort of a substitution to turn it into a nice form. And there are tons of these. There are tons and tons and tons of these, and we're not going to talk about all the different possible cases, but you'll see sometimes in the homework they give you one, and I'll often give that to you as a problem just so you can experience it. So, and this is where we really like having people have gone before us.
Because it's the people that went before us that saw this and figured this out and went, oh, you know, for this pattern, there's this trick, and we don't have to develop it all over again. But it makes us have to pay attention to, is this one of the forms that we know? Is it a nice form? Can we get where we need to be? So, but now you can totally see why I call this monkey math, right? Like the majority of these problems, 95% of the problem is just doing the algebra. It's following the recipe and going through the steps. And you get those real brief instances of excitement. Yay, we're integrating, right? But other than that, it's just algebra, 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 algebra. What form is this? Oh, okay, this is the trick I'm going to do, blah, blah, blah. All right, so good for homework questions. Anything else we want to look at? No? All right, well, then we're going to continue talking about what we were doing last time, which were the exact differential equations, but the ones that weren't exactly exact, but we could make them exact by throwing on that integrating factor. So another really common trick, like we've seen a bunch of times, we multiply by something that's unknown. So let me just kind of remind you about what it means to be exact, and then that process, the multiplying factorness, how that makes it exact, and then we'll kind of go from there.
All right, so what does it mean for a differential equation to be exact? Well, those were the ones that we could write m dx plus n dy is equal to 0. But what made them exact was that the my is equal to nx. So when you take the partials with respect to y and x of m and n respectively, that they are equal. Now, if they're exact, how do you get the solution?
Integrate with respect to m and n. Add them together for the potential equation. And then
Right.
that equals c.
Good, Brandon. So what we're looking for is the potential function. That's the function whose partial with respect to x is m, and whose partial with respect to y is n. Right. So in the language of linear or vector calculus and stuff like that, we're looking for f such that the gradient of f is equal to mn, and then the solution is f of xy equals c. So let me give you an example. An example of one of these would be something like 3x squared y times dx plus x cubed plus 1 over y dy equals 0. So it's of the right form, right? An m dx plus an n dy. And then we can confirm that it's going to be exact by doing the real quick. My here is 3x squared, and x is also 3x squared. So basically, we just need to integrate these with respect to x and y respectively, put them together, and that gives us our potential function. So the 3x squared y, when we integrate that with respect to x, we get x cubed y. You go to the n and integrate that with respect to y, we get x cubed y, which we already have, plus natural log of y. And then, of course, that equals c. And so that would be our solution. So really easy when they are exact. We know exactly what we need to do, and we're good to go. Okay, but they're not always exact. But we did see that we can sometimes make them exact when we multiply by an integrating factor. So this was the trick with those, is we create an integrating factor that we called mu. And it's a function of x and y. We always just write it as mu, but it's a function of x and y. And what we saw is that there were some good situations for this. And here's how we decided that mu. We looked for one of these cases. So the case one was where my minus nx over n is a function of only x. So if when doing this, my minus nx over n is a function of only x, then mu, that's going to be equal to e to the integral of my over n minus nx over n dx. So that's a good situation. The second case, which is just as good, is where if we reverse it, nx minus my over m is a function of only y. And in that situation, we saw that mu is equal to e to the integral of this thing, but integrating with respect to y. And I'm pretty sure, I don't remember 100%, but I'm pretty sure that we did an example of each of these, right? Where we saw that both of them work.
Yeah.
Okay, so we like these. They're pretty quick. They're not terrible, just a matter of doing it. Okay, but there's a third case. We definitely need to see some examples of this, where the integrating factor, where this my minus nx over n and all that is not a function of only x or only y. And so the other case is going to be case 3, which is just as good. It'll work for us, is this. It's where that my minus nx can actually be written as some function of x times n minus some function of y times m. And if we can do this, if we can write it in this way, then what mu is going to equal is going to be e to the integral of px times e to the integral of qy. So it looks a bit uglier, but I wanted you to notice that case 1 and case 2, the first ones we did, are actually just specific cases of case 3. Because think about this first one, where my minus nx over n is a function of only x. Well, if it's a function of only x, there's none of this qy business. You cover that up, and you can see that when you divide by n, you've got my minus nx over n is a function of x. And its solution then is e to the integral of that guy, p of x. All right, well, the other case where it's only a function of y, cover this piece up. If I divide by negative m, that changes the signs on this, which inverts them up here. And again, we get the q of y is equal to this thing, so our solution is e to the integral of qy. Now, I'm not going to bother proving to you that this works. I'm going to have you trust me, or we can at least talk it through. Because these two are the individual mu's down here. And since we're subtracting, it's adding. We've already seen that you can get solutions to sums of equations by taking them individually and putting them together. That was one of the very first things we proved way back when. And this is another case of that. All right, so let me show you how this works. What you can do to show that your my minus nx actually can be written this way, and then how you can find the solution. So here's an example. Let's go with y plus xy times dx plus x times xy dy equals. So the first thing you should do here always is go ahead and see if it is exact. Because if it's exact, we're good to go. So always do that check. So we're going to do my, that's going to be 1 plus x, and then nx, 1 plus y. So it's not exact, but this step wasn't a waste of time because we still want to take a difference of those two. So let's see what that is then. So my minus nx, that's just going to be x minus y. All right, so this is going to be able to be turned into an exact with an integrating factor if I can write this my minus nx as some function times n minus some other function times m. So the question is there a way that I can define P and Q such that this is true? So this is where the work's going to come in, is trying to figure out Px and Qy. So let's start here. Notice that my result of this multiplication is linear. I've only got x and y. I don't have x squareds, x cubes, y squareds, y cubes, which suggests that these P and Q have to be constant. Because let's say P was linear, right? Some sort of mx plus b. When I multiply that out, I'm going to get an x squared term, which none show up here. And similar argument over here, it would give me y squareds, and I don't want those. So P and Q look like they should be constant. So that's the first thing you should do, is try to figure out what kind of form these P and Q need to be. Try polynomials first. They tend to be the ones that work the best. But obviously put in what you need. If you need a log, put in a log. If you need a sine, put in a sine, and so on. All right, so this suggests constants. So then what I'm looking at is I need x minus y to equal a times x plus xy minus b times y plus xy. So let's see what this suggests a and b are. So if I distribute that out, I get ax minus by plus a minus b times xy. So for these to work out, a has to equal 1. For the second ones to work out, b has to equal 1. And notice that if a and b are both 1, 1 minus 1 is 0. That term goes away. And so we're good. So here's where we are then. I've got P of x equals 1 and Q of y equaling 1, which means then the mu I want is going to be e to the integral of 1 dx times e to the integral of 1 dy, which is going to be e to the x times e to the y, or e to the x plus y. So my speaker is acting funny? What do you mean by that, Mike?
It seems to be good now, but it was like a here and there.
All right. So there's our mu. So let's rewrite this differential equation with that mu as a multiplier. So we're going to have e to the x plus y times y plus xy dx plus e to the x plus y times x plus xy dy. Now I'll leave it to you to see that this new m and this new n if you differentiate the first with respect to y and the second with respect to x, gets you the same thing. So I'm just going to jump to integrating. So let's integrate this thing with respect to x. And what we end up getting is xy e to the x plus y. Basically just do parts. So then we'll do the other one with respect to y. And it turns out that you get exactly the same thing. Notice that only the roles of x and y are swapped in these two integrals. So in their two solutions, swap the x's and y's, you end up getting exactly the same thing. Well, now we've got our implicit form. We've got xy e to the x plus y equals c. And there's a solution to this differential equation. So the struggle is going to be finding the p's and the q's. What are those functions that we're multiplying to the original m and n to get us the form of my minus nx? But if we can do that, that integrating factor is going to work just like the other ones did. It's just this is a little bit more complicated structure, which makes sense. All right, so what do you think about that? That's what I thought.
It's a lot of, nah, okay, here's the process. And you can already see that it's going to be long and there's going to be a lot of algebra. But hey, welcome to differential equations, right? And really the idea here, just like always, is the technique we have doesn't work. So let's try to make something that works. And in the process of doing that, it turns into a bunch of algebra, which, while tedious and a pain, at least gets us to we're able to do it. And a lot of math, by this point, you guys have gotten there, hopefully, where you go, yeah, it's about can we do it? Not is it nice, but is it possible? And that's what we're always looking for in math is there a way to make this work? And in this situation with integrating factors, yeah, there is a way if we can write that my minus nx as a product of the original m and n. Yeah, I know. Now you're also seeing why I'm not a huge fan of differential equations, why I chose not to go down this path of math, right? Math eventually breaks into two pieces, and I think I told you this, and Larry probably has. There's the applied math, and there's the pure math. So pure math is like the theory of linear algebra, abstract algebra, which breaks down stuff even further. This is math just for doing math's sake. The applied math, of course, is trying to apply it to things, but applied math, like the start of that is differential equations. And it kind of permeates throughout. I did not like this branch. I took as little as possible. I went down the, hey, let's just do math for the hell of it because it's a puzzle. So that's me, but I know a lot of you like the applied, and I'll just tell people like, you know, like Wes, for you, for example, going into computers, it's all going to be the applied side. Like that's what you're going to be doing. Right. And also for you guys that are going to go into the engineering, the math you're going to do is the applied because you're using it. Right. Which, cool. If that's what you like, that's what you like. It just doesn't do it for me. Anyway. All right. So exact equations are awesome. If we can make it exact using integrating factors, that's just as good. It requires a little bit of work, but once we can get it set up, then we can just go ahead and find the potential function and call it good. All right, so we are pretty much at a point where we're done now with chapter 2. So chapter 2, think about what it was. It was introducing you to all kinds of different types of differential equations and how we solve them. So we've kind of gotten the tools now for solving differential equations. So obviously the next step is let's apply it. Let's actually use this for real things. So we're going to skip chapter 3. If you're curious, chapter 3 is all about using numerical methods to approximate solutions. Again, not my kind of thing. People that use that though are computer scientists, where we set up our technology so that it can get us approximations. But I'm going to skip all that just for the sake of time, so we can do more of the theory behind differential equations this quarter. So we're going to jump into chapter 4. And chapter 4, we're going to start talking about different applications. What are different things that we can use this for? And we've already seen some. Right? We've talked a little bit about exponential growth. We definitely talked about logistic growth, right? So where we have exponential growth, but with a carrying capacity. And then we did that problem where we had the infectious disease that we were also curing at the same time, and what that did to our solution. But we're going to kind of go down that path and look at other kinds of applications. So we have about another 20-25 minutes today. So I'm going to just start with some basic applications of these first order differential equations so that we can start seeing why we care. So for those of you who have been waiting for the yeah, but why, this is where we're going to start seeing it. So the first one actually is exponential growth and decay. So let's talk about the difference between them, why they end up giving us the same formula, and tie this back to some other things that you've seen in physics classes and previous math classes. So I'm going to go back to the board.
So let's start making kind of our list of different applications. So I'm just going to write here applications of first order. They don't have to be linear necessarily. Some of them will be, some won't. But these are just going to be different applications of first order differential equations. So again, remember what first order means. These are ones that have just a derivative. All right, so the first set are exponential growth and decay. So you may remember with exponential growth, we saw that the differential equation was linear, and it was really, really simple. Now, just be aware, I'm going to start writing Q instead of Y, because that's what this textbook likes. Q for quantity. It's the quantity of whatever the thing is that we're looking at. But what we saw for exponential growth was that Q prime is equal to K times Q. We wrote it as Y prime equals K times Y. But this was linear, it's separable. We saw that when we separated it, we got Q equals CE to the KT. So whatever that K was shows up right here, and then we had our arbitrary constant. And then if we actually made it so we had an initial condition, so let me write here, Q of T naught equals Q naught. That Q naught ended up giving us the C. And what we would get for our solution here is Q is equal to Q naught e to the K times T minus T naught. Now, we never had this like T minus T naught. We always incorporated it into the C. But you can just think of this as a transformation, it's a shift from 0. So since we have a shift from 0, we're going to put that as a T minus T naught. So we've done a bunch of these. I don't really want to talk about solving them because you already know how. But the things that I do want to point out, first of all, that K is kind of a big deal. If K is 0, or bigger than 0, sorry, this is where we get growth. So when that K is a positive number, that leads to growth. And when K is negative, it leads to decay. Again, I know you already know this. You can see it in the solution. If we've got e to the kt, if that K is positive, that's a positively growing exponential. If it's negative, it's a decaying one. But you can also see that in the original differential equation, right? Think about what this is saying. This is saying the change in that quantity, it's proportional to how much is already there. But if K is positive, that means our quantity is growing because we have a positive slope, positive derivative. Where if K is negative, then we've got a decreasing function because of the negative slope. So that all makes sense, and it all matches no matter where we look at that K. But this was really the only difference between growth and decay. So if we're going to talk about, you know, a population of bacteria in a petri dish, K is going to be greater than 0 because it's growing. If we're talking about, you know, a bunch of radioactive cesium, the K is going to be negative because it's going away. But either one, we use the same formula. This is the power of the PERT formula, right? Is that it can be used for lots of things. Now, before we step off of exponential growth and decay, I want to talk about half-life a little bit and how it's related to this original differential equation. So you remember half-life? The idea, right, is that it's the amount of time that it takes for half of the original amount to have decayed. So if we talk about half-life, basically it's the time Q to get cut in half. Now you probably know from your time in chemistry or physics and things like that, that half-life doesn't depend on how much we start with. It doesn't matter when we started or anything like that. So let me show you that. Let me show how the differential equations show that as well. So let's do this. Let's say we started with Q. Half-life is going to be when that original, let's call it Q naught. So we started with Q naught. When that original Q naught gets down to half of the K naught, or half of the Q naught, sorry. And what I want to do is I want to actually solve for the half-life. And the half-life is this. It's the T minus T naught. Because we're going to find out how much time has passed. So let's think of that as a delta T. So if I divide by Q naught, I'm going to get 1/2 equals E to the K times delta T. I'll take a natural log. So I get the natural log of 1/2 is equal to K times delta T. And then solving for delta T is 1/K times the natural log of 1/2. And this is actually the formula for half-life. If you go back to your chem class or wherever you saw half-lives, and you were ever just told, here's how you calculate the half-life, this is why. The math says it must be so. Also notice that everything is going to be fine in terms of the signs, plus or minus signs, because natural log of 1/2 is negative. But remember, our K is negative if we've got decay. So that's going to end up being a positive value. What you will see sometimes in books, because some of you may look at that and go, oh, that's not quite right. There should have been a natural log of 2. If instead of thinking of K as negative, and we just look at K as what the negative value is. So like if this was to the -2, instead we think of k as 2, then this would be the natural log of 2. It's just a little fiddling to allow for the sign difference. But here's your half-life. And again, it's kind of interesting that it doesn't depend at all on how much we had initially. It only depends on that decay rate. But that's why some things have a really long half-life and some have a really short half-life, right? Like you know about this probably from radioactive dating. If we want to age a fossil, we're going to use something different than if we're going to try to age a rock. Because rocks being so much older need something with a long half-life. That's why we use something like lead-210 versus like a fossilized leaf, we use carbon-14 because it's a much shorter half-life. All right, so, excuse me. The most basic application for the first order, but a really big one. It's used in lots of places. I mean, it's even used in money when we talk about things like compound interest. You remember compound interest? That's a real, do you remember? Kinda. So I'm going to put this as another example, but maybe we're going to call it 1A because it's kind of related. But compound interest So compound interest, this is another situation where your money earns money. And you may remember that there was a formula for this that looks something like this. Now, when you saw it, you had different letters. Like the Q naught was a P for principal. This Q was probably an A. But I'm going to go ahead and kind of write this the way that, with the same letters. So Wes just put up here PERT, the PERT formula, if it's continuous. We're going to prove that actually. We're going to prove that you actually get the PERT formula. So the way that this plays out, Q naught is the amount that you initially invest or borrow. R is your interest rate. N is the number of times that you do a compounding per year. And then T is the number of years. So like you can compound interest monthly, N would be 12. Daily, N is 365. Quarterly, every 3 months, N is 4. So that can change. But one of the things that was of question is what happens as N gets really big? What happens as N goes to infinity? And back in the day, and we're talking thousands of years ago, they saw that there was a pattern, that there was a limiting value that you could not get more than. They didn't have the tools to do it. They knew roughly what the number was. But now we have the tools. So let's take a look at this and see if we can figure out what the limit is as N goes to infinity of this thing. So first thing to notice is that R, it's going to be fixed, as is T, right? As is Q naught. So the only thing that's changing is N. So we'll pull that Q naught out. And then we're going to look at a limit as N goes to infinity of 1 plus R over N to the N. And then we're going to take that limit and we're going to raise it to the T. So we're just making use of the rules of limits. So now I want to know, what is the limit of this thing in the brackets?
1 over E. No.
Well, let's just try plugging it in, right? You plug in N equals infinity. So R over infinity is 0. So 1 plus 0 is 1. So we get 1 to the infinity. Well, the problem with 1 to infinity is it's one of the indeterminate forms, like 0 over 0, infinity minus infinity, right? There are a whole bunch that we just don't know. And 1 to infinity is one of those. So we are going to have to do L'Hopital's rule. Okay, but in the form 1 to infinity, L'Hopital's rule is no good. What we actually need is either infinity over infinity or 0 over 0. So this is one of those where you have to do a little trick. So first things first, I'm just going to call this, say, A. A is going to equal 1 plus r over n to the n. So I'm going to take a natural log. And what that allows me to do is bring the n out front as a multiple. And if we plug in infinity for n here, we're going to get infinity times the natural log of 1. The natural log of 1 is 0. So now this is infinity times 0, which is also indeterminate, but we know how to take care of that. We can just divide by one of those two, by the reciprocal of one of those two. So let's write this as natural log of A equals natural log of 1 plus r over n over 1 over n. And now we've got 0 over 0. So let's apply L'Hopital's rule. So L'Hopital's rule, we just differentiate top and bottom. So we'll start on the bottom. It's easier. N to the minus 1 is going to give me a minus 1 over n squared. On the top, since I have a natural log, that's going to give me a fraction. The bottom of the fraction is going to hold what's inside the log. And then the top is going to hold the derivative of what's inside the log. So the derivative of 1 plus r over n is minus r over n squared. So it was just chain rule. All right, well, now we need to simplify this. If we flip this bottom fraction over and multiply, the minus signs cancel, as do the n squareds. So we're left with r over 1 plus r over n. And now if we let n go to infinity, the r over n goes away, and we're left with just r. Right? So this limit, as n goes to infinity, equals r. But now we got to go back and realize that this isn't the limit we were looking for. Right? This is not the limit you're looking for. Because we want to know about a. What we just found is the natural log of a. So what we know then is that the limit as n goes to infinity of 1 plus r over n to the n is actually going to equal e to the r. Right? Because that natural log, we got to take e to that power. All right, so long story short, if we go back, remember that this was part of the original limit. And what we had was that Q was equal to Q naught times this limit. Let me just rewrite it and then we'll put in what we found. So we just calculated that this limit is actually e to the r. So this is Q naught e to the r raised to the t, which then by the rules of exponents gives us Q equals Q naught e to the rt. So it's a completely different kind of thing, right? I mean, we're looking at money growing continuously. but it leads to exactly the same problem, the same solution as exponential growth and decay. So we can kind of reverse engineer this then, and we can think of the differential equation that this would have come from is q prime equals r times q with the initial condition of q of naught, or q of 0 is equal to q naught. So if we want to talk about continuously compounded interest, it's exponential growth where the interest rate is our k, it's our growth constant, which kind of makes sense. Like if you think about it from the population standpoint, we're getting a rate of change that's proportional to the amount that's there. Well, yeah, you're going to get more money if you've got more money in the account. So even though it feels completely different, it's exactly the same. And I guarantee that those folks back in, like Babylon back in the day would have loved knowing this instead of just having to go with, well, we know there's some number around 2.7 something that works. All right. So I think I'm going to stop here.
And what we'll do next time is we'll continue to look at examples, and we'll start looking at ones that are a little bit more complicated. Like, what if we are, like, take a money example. What if we've got an account that's earning interest, but at the same time we're taking money away, right? So like this is an endowment fund or something, and we want to take money out for scholarships. What's that going to do to our equations? We'll start looking at what we call the pond problem, which is, suppose that you've got a pond and there's a pollutant that's coming into it. How do we figure out how much pollutant is there if we know how it's changing, and the like? So we will continue with applications, and we'll just keep seeing why we care about differential equations.